Tide strongly believes the importance of environment protection and energy efficiency in order to achieve a sustainable future for mankind. Thus, our technological commitment will foster mutual betterment of our allied companies, customers, shareholders, and employees. Tide pledges to always hold our management philosophy and values at heart. Until now, the meter readers have had to do manual meter reading. This existing manual process is time and money consuming work. This makes it hard for us to detect blackout and manage energy demands. And it makes us hard to manage loss during transmission and distribution. As a result, this existing manual process makes grid unsmarter. But Tide's end-to-end AMI solutions will connect the user with utility companies. Tide's intelligent AMI solutions will solve many problems from the existing manual process. We can reduce time and money spent metering manually. We can manage blackout and loss during distribution. We can do demand response, TOU. Finally, we can make grid smarter. AMI service. Meter reading information of household is call-cited by modem and DCU. There are two types of smart meter, internal and external. Smart meter sends metering data to modem via serial communication. Modem sends metering data to DCU via PLC communication. DCU sends metering data to server via fiber optic and cellular network. On-time monitoring and detection of electrical loss. TOU, time of USA flexible tariffs. Connectivity to electric vehicle charging system. Connection of renewable energy and battery with bidirectional metering. Reliable collection rate improving monitoring of power quality. Making grid smarter and more efficient. A hidden champion in the energy IoT solution industry. Tide.
know where the light comes from? Tonight, I'm going to tell you a story about the people who keep the lights turned on all around the world. One of the most important things in our lives is electricity. It's invisible, but it heats our home, lights your school, and powers the train that takes your parents to work every day. For your light to work, you need electricity. This electricity travels a long way to get to you. Imagine a massive spiderweb that covers the city and the whole country. Electricity travels through the spiderweb to turn on your bedside light. Adults call the web the electrical grid. It's the biggest machine ever built. It's what connects and powers all the other machines. First, we collect the electrons that come from nature or from big factories that make electrical energy from wind, water, sun, coal, or gas. Then we transform and transport these electrons through the machine. A tough job. We constantly reshape this energy to fit the journey it will take to reach its destination. And then we control the machine. We make sure the electrons find the best path through the spiderweb and deliver it safely to every corner of the planet. The need to keep electricity flowing never ends. There is so much work to do to keep the electrons flowing all over the world to light the homes of little children just like you. That's why I'm so proud of the work I do every day to help make all this happen.
The various stakeholders in the French smart grid sector may be found on this diagram: network management and operations. These solutions deliver cost savings and technical improvements to networks. New uses. These solutions encompass e-mobility, smart homes and smart buildings. Of the prosumer. Prosumers are active participants in the energy market, thanks to smart meters and self-consumption. Integration of renewable resources. These solutions help manage the challenge of renewable energy intermittency. Use of data. Energy data is put to use to offer new services to consumers and local authorities. Research and expertise. Members of this sector offer smart grid-related training and consultancy services. France, including overseas departments and collectivities, aims to generate 32% of the energy it consumes from renewable sources by 2030. Since 2008, 121 pilot demonstration projects around the country have helped hone France's expertise in smart grid operational technologies and features. From 2008 to 2014, €500 million has been invested in R&D, putting France top of the European League. Now, this experience and the French government's call for proposals for large-scale smart grid projects has resulted in projects being rolled out in several regions by the successful applicants: FlexGrid, UNGrid and Smile. These smart grid projects span several regions and focus upon the 6 key aspects of the French smart grid sector, promoting French expertise in this field on the international stage.
Okay, ladies and gentlemen, may I have your attention, please? The webinar is about to begin. Honorable speakers, distinguished guests, ladies and gentlemen, good afternoon for those who joined the webinar from all around the world, especially from Indonesia. Let me introduce myself. My name is Hardimasyar, VP of Technology Development at PTPLN Persero. On behalf of the Indonesian Electrical Power Society, Masyarakat Ketenagalistrikan Indonesia, or MKI, I would like to welcome you all to the 5th episode of webinar entitled of Wide Area Monitoring, Protection, and Controlling. This webinar is supported by PTPLN Persero and sponsored by Tide, Huawei, KEPCO, Hitachi ABB Power Grids, Siemens, ABB Sakti Industry, Trillian, GE Grid Solutions, Wärtsilä, LS Electric, Mitsubishi Power, PT Indonesia Comnet Plus, Icon Plus, and in partnership with Think Smart Grid France and Energy Academy Indonesia, or ECADIN. If your company is interested to be a sponsor or speaker in the next MKI Webinar Series on Smart Grid, feel free to contact us at mki.secrt@gmail.com or fill in the form that we have provided on our Zoom chat box. Today's webinar is the 5th episode of MKI Smart Grid Webinar Series out of 10 episodes hosted by the Indonesian Electrical Power Society, Masyarakat Ketenagalistrikan Indonesia, taken place in April 2021 until January 2022. Utilities are facing challenge to keep up with the technology development in order to be able to provide a reliable, robust, and affordable electricity services. Therefore, the global power company start to improve its resilience, reliability, sustainability, and capability of its dispatch system from SCADA to wide area monitoring, protection, and controlling. For improving the system resiliency, WAMPAC will provide the capability on real-time data usage by monitoring, assess, and automatically take the necessary control action to prevent or mitigate problems. Today's webinar will feature experts from around the world to share the latest advancement, benefits, and deployment of wide area monitoring, protection, and controlling in power system. Okay, before we get started, I'd like to go over a few items so you know how to participate in today's webinar. You will have the opportunity to submit text questions to today's presenters by typing your question into Q&A box at any time during the presentations. Please mention your name, organization, and to whom the questions are posted. We will collect the questions and address them during our Q&A sessions. As you all know, there will be 2 Q&A sessions in this webinar. There will be a presence form posted on chat room in Zoom and live chat in YouTube. Please fill in. You will receive an e-certificate for this webinar participations via email within 7 working days at the latest. The webinar presentation materials will also be sent to your email. This webinar is also live streamed via YouTube channel MKI IEPS and remains there after this event finishes. As a request from the organizing committee, we will have a photo session with all speakers. So please, all speakers, switch on your camera for a while, for 5 or 10 seconds. We will count down 3, 2, 1 for taking a picture. Are you ready? Okay. I will start to count. 3, 2, 1, smile. Okay, we are done. So now we would like to introduce our keynote speaker, Pak Haryadi, a Director of Corporate Planning at PTPLN Persero. And without any further ado, I would like to welcome Pak Haryadi to deliver the keynote speech on WAMPAC in Indonesia. So, Pak Haryadi, the floor is yours.
Thank you, Moderator, Pak Tri. I will try to share my presentation first. honorable speakers, MKI committee, all the participants, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Today, we would like to present our keynote speech in MKI Webinar Smart Grids with the title of Wide Area Monitoring, Protection, and Control. Now we will start with the energy trilemma and the transition in Indonesia. Recently, the utility company and energy industry over the world has two main challenging issues. The first is trilemma energy, how we provide energy and electricity in efficient within the affordable price, how we produce electricity on high quality and reliable, and how we do our business to sustain using much sustainable resources such as renewables energy. Indonesia energy trilemma consists of the first is related to the efficiency or affordability. Until now, the losses of the transmission and distribution is still higher. It's around 9.32%. In distribution is 7.24%, and the transmission is 2.25%. Asian average is just only 7.37%, and the global average around 8.14%. The LCOE also still relatively high, is around 10 cent dollar per kWh. The second one is reliability. Now the quality of the product is still very low. The SAIDI is around 18.95 hours, and SAIPI is around 11.51 times. If compared with the ASEAN SAIDI, it's just only 10.72 hours, and SAIPI is around 8.71 times. And the third one is related to the sustainability. The power utility now in Indonesia is contribute around 33% in CO2 emission. If compared with the global, is still okay. The global is around 42%. In Indonesia, CO2 emission is around 195.9 million ton CO2 in 2019. Electricity production is still dominated by fossil fuels, is around 88.67%, and coal around 66.55%. Gas 21.99%, and fuel oil just only 4.23%. But the renewable energy mix is just only 11.33% until now. At the same time, we also deal with the global energy transition driven by 3D. If you see here, there's the carbonization, digitalization, and decentralization. By 2050, electricity becomes the central energy carrier. Gross electricity consumption would more than double. 85% will come from renewable power. The grid should be more flexible to integrate with mass RP and all energy resources. Both challenging issues put the grid to be more flexible, efficient, reliable, resilient, and sustained by utilization such as ICT, information and communication technology along the utility value chains, and highly customer engagement. If we talk about the smart grid solution, why we need a smart grid as a solution? It's because of its main functions will cover improving efficiency, reliability, resiliency through automation and digitalization along the utility supply chains. All we call it digitalization. And also the engagement and empowering customer to be prosumer is related to the decentralization and also increasing renewable energy penetration by enabling grid flexibility that all related to the decarbonization initiative. Anyway, smart grid is your concept from power generation, transmission, distribution, retail, and customer. It includes some technologies such as energy storage system, advanced metering infrastructures, distribution automation, and WAMPAC, what area monitoring, protection, and controlling that we talk today. And also there is a mobility or electric vehicle infrastructure, predictive algorithm, and so on. One of the main technologies smart grid is WAMPAC, which is implemented mainly on the transmission network. Based on that, PLN already had a smart grid roadmap consisting of 2 stages implementation. Short stage for achieving the basic function and the long stage for achieving the ultimate goal of smart. We put WAMPAC at the second or long stage, which will be implemented from 2025. The objective is for improving the grid system reliability and resiliency to perform self-healing capability of the grid. Here we talk about WAMPAC system, but it can be seen from the figures. Line and the transformer protection from the first layer here is a basic relay protection system in the transmission network. Relay protection act locally and on element levels, such as in a substation, and usually cover just one element. Therefore, only a limited quantity of data is being exchanged between different protection devices. What area protection device from a second layer, its basic functionality are synchronized measurements, local protection function, and input or output module. For swing and out of step condition in transmission network are very demanding for protection and control system to detect and properly react. The third layer is a complete power system control with wide range of manual and automatic protection picture here. It's also including the SCADA functionality. This layer is connected to other 2 subordinate layers, and it uses as hub for central control visualization of all the available gathered data that will become increasingly important with flat penetration of variable renewable energy in the PLN power system. Why we need WAMPAC? As a main part of smart grid, WAMPAC play an important role for dealing with the stability, reliability, and also resiliency of the grid. WAMPAC has many beneficial for the improving the grid system by overcoming an imbalance between generating power and load, detecting a contingency on the large grid system, capability for doing a very quick response, supporting for load and generation shading mode, fully support to perform an island operation, able to prevent widespread interference blackout, and also improving process recovery after interruption and synchronization. However, for implementing WAMPAC in Indonesia, especially in Jamali grid system, we have several issues as follows. First issue, WAM is not able to fully observe the Jamali grid behavior, yet because the number of PMU is still limited. Second is the WAM storage capacity server currently is not sufficient. It already reached around 100% capacity now. The third one, the existing PMU are not able to analyze and detect the system oscillation yet. The fourth one, the existing WAMs doesn't support integration with adaptive defense scheme to become a WAMPAC yet. Now we have start to develop this adaptive defense scheme in a Sankara system, and we hope in the near future it will be operate well, and then we will be connected with the WAM system and make it WAMPAC is possible. The fifth one, the existing 35 PMU unit is only being processed by one set now, redundant pressure data concentrator at JCC Gandul. Another issue is related to infrastructures. Until now, no study has been conducted to upgrade WAMPs to WAMPAC and determine the location of the BMU. There is limited space also at substation for installing new devices. And the last but not least is a budget limitation. It also always another handicap is financial constraint. And the last related with the people's PLN now is no capability for conducting the study of WAMPAC implementation or upgrading WAMP to WAMPACs. Related to we still don't have enough SRD resources, and now the existing PLN operators engineers also need a special training to be able for doing operation and maintenance of all. And the last is PLN is also capacity building to increase knowledge and skill of engineers who handle the existing WAMPs. Eventually, we hope this webinar will give a contribution and support us for implementing WAMPAC in Indonesia effectively in the near future. Thank you very much for your attention. Stay safe, stay healthy for all of us. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Pak Haryadi, for the inspiring speech on WAMPAC in Indonesia. So as delivered by Pak Haryadi, I would like to make a summary on the presentations. Indonesia right now is facing the energy trilemma: affordable, sustainable, reliable, and energy transitions, digitalization, decentralizations, decarbonizations, and it is pushing the utilities to improve the efficiency, reliability, resiliency through automations. One of the main initiatives in the Smart Grid Roadmap is upgrading the capability of control center into wide area monitoring, protection, and controlling system by 2026, and so on. In addition, Pak Haryadi elaborates the benefit of WAMPAC along with the challenge in terms of technical issues, infrastructure issues, and people. Well, we have one question for you, Pak Haryadi, before you move to another important agenda. The question is, what is the most urgent thing that PLN need at this time to develop WAMPAC according to the roadmap that has been made? Please, Pak Haryadi, answer the question.
Yeah, of course, we will need the WAMPAC implementing in our system now. If we see now, the problem or the challenge in power system is become bigger and bigger, especially if there is a huge or a very intensive penetrating renewables in our system. And also another challenge is about the limitation of the operations limit, because of in some case we have some problem for building new transmission line, new power plant that will be have a good location in some place. We put this far from the load, and we don't have enough transmission line to send the powers and make it very a weak connection to the loads, and this make it the operators have many difficulty to manage the system with huge or spare of errors. It just only have just a small portion of error. It means we need real-time monitorings. We have built first WAMPs before we build the WAMPACs, because in WAMP we can make monitoring real-time, but still the protection or the control measures still related with the operators. But if we build the WAMPACs, in some portion we can rely on protection device that can we operate very fast, then we rely on the operators. I think my opinion for why PLN need this WAMPAC for the near futures, not only just the normal protection device and also WAMPs. That's all, Pak Tri.
Okay, thank you, Pak Haryadi, for the response. I think the challenge that you mentioned before will be covered and discussed in the later forward presentations from the experts. And thank you for sharing with us, Pak Haryadi. Thank you very much. It is a great honor to have you today in webinar. Thank you very much.
Okay, thank you, Pak Tri. Thank you, everybody.
Okay, so let's move forward to our next agenda, which is a presentation from Mr. Sankara Subramanian from GE Grid Solutions. Again, I would like to remind you the attendees or participants have the opportunity to submit text questions to today's presenters by typing your questions into Q&A box on Zoom or via live chat in YouTube at any time during the presentations. Please mention your name, organizations, and to whom the questions are posted. We will then collect the questions and address them during our Q&A session. But before the presentation begins, it's my pleasure to inform you a brief biography of Mr. Sankara. Mr. Sankara has a strong academic background with 30 years of experience in electrical power system and grid application engineering, product management, automation services in various technology leadership roles, driven by passion and vision for future solution strategies on one hand and focus customer requirements on the other. He is a GE Fellow Expert Community with 13 granted patents. Recently, Mr. Sankara is a Global Transmission Service Manager based in UK. And without further ado, I would like to welcome Mr. Sankara to deliver a presentation about system integrity protection schemes. So please, Mr. Sankara, you have 15 minutes. The Zoom is yours.
Thank you. Thank you for the introduction. Given the time limit that we have, I would rather straight jump into the slides. Yes, in line with today's topic, system integrity protection schemes is the other name that we have for WAMPACs, and so I would straight away jump into the topic of why we need system integrity protection schemes. Now, to understand the need of that, we know the reliable criteria that has been employed by most of the transmission planning and operation operators in the majority of the power systems is the N-D criteria, which requires a transmission system to be developed and operated at all the load levels and also to meet the most severe double circuit contingency, and in addition to any scheduled outages. Now, given with this requirement, reliability criteria, now with the increase in the generation as well as the load generation due to the renewable integrations that we see, as well as with the demand in the loads increasing, and keeping up with the above criteria in a short term would then require one of these two alternatives. A, reinforcing the infrastructure, which is a most expensive alternative. B, more intelligent use of the infrastructure, which is basically the wide area monitoring system integrity protection schemes. To understand the impact of the power outages that has been costing globally, and estimate is around 350 billion annually, both in productivity and the loss of businesses. That sets the need of why we need system integrity protection schemes globally. Now, what is system integrity protection scheme? The IEEE definition goes as follows: a customized solution for utilities to detect disturbances occurring across interconnected networks and take actions to prevent the disturbances from cascading to other networks within milliseconds. And this is key. Now, in terms of the SIPS worldwide experiences that GE has been executing for over a decade and a half or 2 decades, is because of these reasons. GE can monitor, control, protect at speeds that cannot be achieved with the central SCADA or the monitoring systems. The reaction times are typically of 200 milliseconds. GE has engineered and validated algorithms for performing the system integrity protection schemes. And most importantly, the global projects and the regional centers of excellence, teams for engineering, executing, and supporting the SIPS project is a real need if we have to execute SIPS of a large magnitude. And there are some examples of the projects that has been listed down here. Over the last 20 years, projects across the globe that ranges from USA to Europe, as well as to the eastern frontiers. So that's the number of projects, a gist of the projects that's been executed and have been in operational successfully over the last decade and a half or so. Now, I would actually, given the time constraint, take in 2 example projects, dwell a little deeper into this, giving a brief of the project magnitude and size, and then maybe also go into the operational experiences of those projects, and then end up with the life cycle of the SIPS as a whole, to give its completeness. So hereafter we will cover briefly on 2 example projects, and so the first example is that's been covered in here is the Salt River project in the US. So the need for mitigation this is an example with Palo Verde Unit 2. The speciality of Palo Verde, we'll see in the next slide. It was operated by 120 megawatts. This then impacted the safe operation of the California-Oregon intertie line, which is 3 into 500 kV lines, and the details as you can see in there. Now, in regards to the Palo Verde in itself, it's a largest nuclear power plant in the Western Hemisphere, and the power plant has got 3 reactors with each of them totaling to a sum total of 3,860 megawatts. And this plant is situated in the transmission corridor that supplies to Los Angeles Basin and the Southern California. Now, loss of multiple units of Palo Verde can cause voltage dips, frequency excursions. So WECC modeled the loss of 2 of these units to determine in its original capability with the stability guidelines, were there any issues with the originally planned generation output levels. WECC region remained stable for the loss of 2 units. No such remedial actions were needed. Now, the problem actually came in when the uprating was made, and that is when the design of those original units allowed for augmenting the output of the generators, and then they were uprated by 121 megawatts. That is when the real need came in. What happened was that with the loss of 2 units caused problems on the power flow of the COI, the California-Oregon intertie. Especially the lines got overloaded and indicated that the frequency dipped to 59.75 hertz. So that is when the real need was there to actually mitigate what happens during the separated supply of this generation. And if there is going to be a loss, how do we mitigate, still maintain the intertie? What do we do to maintain this? That's when the mitigation studies were done. And it showed that if we were to mitigate this extra 120 megawatts that has been operated, and the loss of these 2 units by performing this load shedding operations, that would actually maintain the system. And so the solution was then decided by the owners that to provide an intelligent system of load shedding in various locations throughout this local area to prevent the inadvertent load shedding just on frequency. They also included the power criteria. And the scheme required relays to measure the generation level of each unit and the sum total of the pair, each pair, which was then compared to a set point equal to the original output of the 2 units. If the paired unit loading was exceeded, and then to provide the arming. So the solution was then worked out, and it was also thought over in order to provide high availability to have the redundant scheme, which is to provide redundant relays and to provide the redundant comms communication channels. And as you may see in the next slide, one of them was over the Ethernet channel, and the other one was over the 64 kbps serial comms via the G703. And this on the 121 megawatts were actually considered to be shed across 14 sites, 14 different sites. And that's the communication architecture I was just mentioning, 2 different architecture, independent architectures, redundant architectures to ensure that there is high availability. Now that's one example. Let's check in the other example. And this is about the project between the Turkey side as well as NSOE, now called the NSOE. Previously was called as the UCT. Now that project was actually the TIA's special protection scheme. The project in itself was named as the rehabilitation of the frequency control performance because it allows the synchronous operation of Turkey with respect to the continental Europe. And so the customer in this case was the Turkish electricity transmission company. The objective was very clear, to get the benefit of the synchronous parallel operation from Europe, as well as integration of Turkey's electricity market into the internal EU electricity market. Now, the slide gives then a glimpse of the stronger 400 gigawatt side of the Europe, as well as the 49.5 gigawatt side of Turkey. And these both were going to be interconnected. And here in itself, there is a, as we can see, there is a cause of a problem in order to make it operational with this interconnection, because if any disturbance were to happen, there will be the swinging of the power flow between each sides, and that was the real problem that was needed to be sorted out with this solution. So the connection of the Turkish EPS to the NSOE by the 3 lines, 2 lines to Bulgaria, 1 line to Greece, ensured that NSOE could actually import to Turkey 800 megawatts. In the same way, Turkey was able to export to NSOE 1000 megawatts. And then the studies that were conducted by the European Union side demonstrated the feasibility of this interconnection, which is quite possible, but then it needed the frequency controlled improvement as a first line of defense, and then as a second line of defense, the SIPs required to authorize this interconnection. So and hence the SIP schemes were coming into force. So in the next 5 slides, what we will see is the overall solution about the SIP schemes that we had to implement in TIA's system. So following with this, so the system had the generator dropping, which is based on the rate of change of active power. And hence in this interconnection between the Europe and Turkey side. So anything were to happen, so Turkey had to do the generator dropping. In a similar way, anything were to happen, load shedding had to be carried out based on the rate of change of active power. And the third one is a very interesting one, which is the inter-area oscillations detector, which is based on the oscillations of the frequency of the active power in the interconnection. Again, there is a specific range. I will go into those details as we move towards the solution part a little more.
Sorry, Mr. Sankara. You
yes.
only have 3 minutes left.
Oh, 3 minutes left. Okay.
Yeah.
So thank you. So that's the so what you see on the top right-hand side, left-hand corner is the blue part, which is basically the solution side and the solution with the components that were needed to connect Turkey with Bulgaria and Greece. And this is a redundant scheme, as you can see from main and redundant. We again implemented via the G703 schemes. Very critically, inter-area oscillations are a special thing to be dealt with in this case, because NSOE being a larger system, Turkey being the smaller system, and we had to deal with the oscillation detectors. And as you may see there, these oscillation detectors were developed way back in 2010 to be employed along with these, with the load shedding and the generator dropping schemes. Now, the whole scheme, we were able to perform the most accuracy because we had the real-time digital simulations, and we have it still at the Center of Excellence based out of Bilbao. And this whole scheme was modeled and then studied and taken care of some of those scenarios, what we would have otherwise faced in real time. So just to give an example, had there been no special protection schemes with the loss of 2000 megawatts, what would happen to this inter-tie is that the system would be oscillating back and forth, and you can see it will still oscillate for a long period of time and may even grow. And with the special protection intervention, there comes a stability within few milliseconds. And I would end up with covering the operational experience. The first one was on July 26, 2011, wherein we had to perform an load shedding, specifically when there was a blackout in northeastern region, and then within 2 seconds after the blackout has happened, the SIPs at the Ahmedabad intervened with the settings exceeding those sum total of active power and the average rate of active power, and then it shed 400 megawatts, thereby ensuring this interconnection. And that's an example what you see with the with what happened as the recording. And for a generator dropping as well, there was an event that actually disrupted 3 into 400 kV lines, and then there was overload, and Turkey was exporting now to the NSOE side, and then 4 out of the 7 generators were then dropped actually to restore this balance or still maintain the interconnection. In summary, the SIPs of this project way back in 2011, it demonstrated a very useful tool to prevent the major events in the power system. The investment is relatively low in comparison to the benefits. A single correct operation, payback, the investment is paid back. SIPs in Turkey has operated successfully 5 times in less than 2 years, and none incorrect operation. And what it demonstrated is that to have a proper and correct project management test plan is vital for the design and validation. And most
Sorry, Mr. Sankara, your time is up.
Okay.
Can you make a final statement?
Yeah, so with the complex interconnected networks, with the growth of the renewables, now SIPs solutions are integral means to ensure the steady state stability of any power system. With that, I conclude. Thank you.
Okay, thank you, Mr. Sankara, for the interesting presentations. I really enjoyed the presentation. Lots of key insight and takeaways. Some of them are increasing the amount of generating capacity and not require one of 2 alternatives. One is reinforce the infrastructure, which is more expensive, and then the second one is implementing wide area monitoring, system integrity protection schemes. Then I noted also power outage costs over $350 billion annually, estimated. That's a big amount of money, yeah? Yeah.
It is,
So,
given taking into consideration all the business losses as well as the energy losses. Yes.
Okay, and also GE has many work and experience that has been done successfully in USA, Turkey, Italy, Spain, France, and UK. There are 2 cases that have been elaborated more in these presentations, which are in South River, USA, and Turkey. And then the last one, System Integrity Protection Scheme, has demonstrated to be very useful to prevent major events and ensure steady stability of power system. Thank you very much, Mr. Ankara.
Thank you. That's a precise summarization. Thank you.
Okay. As a reminder, the attendees have the opportunity to submit text questions to today's presenters by typing your questions into Q&A box on Zoom or via live chat on YouTube at any time during the presentations. Please mention your name, organizations, and to whom the questions are posted. We will then collect the questions and address them during our Q&A sessions. Okay, so let's move to our next agenda, which is a presentation from Siemens AG, Mr. Christian Romeis. But before the presentation begins, allow us to read a brief biography of Mr. Christian. Mr. Christian Romeis got the Diploma Engineer degree in Electrical Engineering in Friedrich Alexander University, Erlangen, Nuremberg, Germany on 2011, and received Doctor Engineer PhD degree in Electrical Engineering at the same university. And before that, Mr. Christian was a senior power system consultant at Siemens AG, Erlangen, Germany. He was a research scientist in Friedrich Alexander University, Erlangen, Nuremberg, for 6 years, and he also a trainer for Siemens Power Academy, an expert on power system protection, dynamic performance of power system, and strategic network planning. And without further ado, I would like to welcome Mr. Christian to deliver a presentation on WAMPAC, is a journey to higher utilizations. So please, Mr. Christian, the Zoom is yours and about 15 minutes.
Okay, thank you for your introduction. So I will share my screen. So I hope you can see my screen now, okay?
Yep, we can see your screen clearly.
Okay, thank you. So as you said, I will present here from a consultancy perspective. So we see here a journey to higher utilization with WAMPAC systems. So from the consultancy perspective, we see maybe you have something in the monitoring, you have something in the protection, special protection schemes, and maybe you want to introduce something, some control schemes. And we see here these 3 parts, and we see in the future that these 3 parts have to grow together. So on my next slide, you have on the left side the monitoring part, wide area monitoring. So you can introduce state estimation, you can enhance your state estimation, maybe to linear state estimation. You also can introduce some alarms and recognitions, maybe power swing recognition, disturbance recognition. You also can learn situational awareness, and you can also do post-fault analysis in the WAMPAC, in the wide area monitoring system. So you introduce some PMUs and so on, and collect all the data and analyze it, and then you can get information out of it. You see the problems. Maybe you can see you have some inter-area oscillations and so on. And on the right side, you have this wide area control. Maybe you can introduce here control schemes for voltage, for frequency, also for damping of inter-area oscillations. So one idea is here, if you use, based on PMUs, voltage differences in different areas, maybe to control the active power flow between 2 areas, and then you can damp the inter-area oscillation. So this can be an idea in the wide area control. So maybe you close the loop from a monitoring system, so PMU data, to incorporate this in the control, maybe into an HVDC control system, a thyristor control series capacitor system, or SVC system, to control or damp these inter-area oscillations. Also, in case of long-term voltage problems, you can start with controlling actions, switching capacitor banks based on wide area monitoring results. And also then after that, you can introduce, if it's dropping down or going down the voltage, can introduce protection schemes then. So followed by these controls, you have protection schemes. And the third part we see is the protection scheme. So here are in this circle, we have these system integrity protection schemes, the special protection or system protection schemes, and also the remedial action schemes. Are in this circle of the wide area protection. And our idea here is maybe in the future you can adapt these schemes with information from wide area monitoring systems or wide area measurement systems, and maybe adapt the schemes to the actual system state. So based changing the load shedding actions, changing the generator rejection, and also maybe changing the action in case of a transient stability problem, so splitting the system at a different point in the network. And also the wide area protection can be a backup protection. So next thing is design goals. We see here some design goals for the WAMPAC system. As you may know from protection, you have the dependability, you have the security, and also you have the selectivity. We also name here the speed. Because in WAMPAC systems, you have to deliver the action in time. So if you introduce a protection scheme, then you have to be maybe very fast in system splitting. And also in control schemes, if you close the loop, you have to be very careful with the latencies, for example, so that the action is delivered in the right time. And on the right side, we see very important for the WAMPAC system and expandability and interoperability, so that you can expand it at any time with different vendors, with different building blocks you might have, you want to introduce, with different applications you want to introduce. And also the accuracy is very important. So here you have to decide if you want to use maybe M class in the PMU or P class based on what your objective is. So for protection, maybe, okay, you use the P class, you need a fast acting system. And for metering or also model tuning, maybe you use the P and the M class plus very precise instrument transformers to get a very accurate result. Also, redundancy is very important. Also, if you have the protection scheme, maybe you have fully redundant scheme, as we saw in the system integrity protection scheme in the presentation before. Maybe you have full redundant scheme in case maybe just of monitoring, just collecting some data, maybe it's not necessary. So maybe you have to think here, okay, what I need and what is needed for the goal I want to fulfill, or which problem I tackle. So just an example from our side about the conceptual design for a WAMPAC system, we see this example has the objective to control the line loadings and island detection and control. And what we see, you have different building blocks. So maybe you can grow from a special protection scheme to the WAMPAC system if you include more building blocks. For example, in this case, just the protection relay trip, then you have the islanded system, then you have some reactions pre-calculated with a lot of studies. But you can also incorporate new measurements, PMU devices or RTUs as a building block. Then you have actuators as a building block. Maybe you can use controllers of the generators. For example, you can maybe also incorporate signals from PMU to the power system stabilizer in case of conventional generation. In case of photovoltaic, for example, you have the ability to curtail these if it's needed, and you also have the under frequency relays for load shedding. Maybe you can say, okay, if I increase my or expand my system with information from PMUs, I also can say, okay, with a central equipment system like a server and controller or protection relay, I can block or enable the under frequency load shedding, or change the feeders I want to shed based on the actual active power. And another one could be to extend the system with external systems, so also interface to a SCADA system, use information from the SCADA system in the central equipment, maybe to identify the actual system state and then change the reactions, maybe change the logics by its own based on SCADA information. Another external system could be also a PDC from a neighboring TSO, for example, which can be incorporated into the system. And everything has to be connected with the wide area network. So you can see in the center, you have this wide area network, must be has a good strength to connect all these distributed devices and also the central equipment together in one system. How to achieve this from our point of view is you have to introduce a clearly defined roadmap. So you have to define what are the problems at the moment with some studies, what are the problems in the future with some studies, and you also have to say, okay, what are the steps I have to implement? So you have to let it grow. This is our idea. Let the system grow together. You can start on the side with monitoring, on the side with control, and also you maybe have system protection schemes, so you can extend and expand the system. And after that, you have to think about your overall architecture or infrastructure you want to use. Also, you need to define all the layers you want to have, starting from the devices in the field, coming to substation. Maybe you also need substation controllers in this wide area monitoring, protection, and control system if you just have local actions to do. If you just have local actions, then you maybe can use on the substation level a controller. And then you can bring it up to the control center level. And you have to think in these layers. And also you have to define standardized building blocks for you. Okay, which sensors I want to use, which actuators I want to use, what should I use in the wide area network, and you need to define key integration requirements. So it just must be flexible and expandable. And also you think about modularity, especially in the case of devices, because you can say, okay, I want my PMU standalone, or I can say I want my PMU in a protection device, for example, because I think most of the vendors have the possibility to have the PMU functionality in the protection device.
Sorry to interrupt you, Mr. Christian. You have
yes.
4 minutes remaining.
Yes, thank you. And one thing is also you have to think about the network protocols you want to use. So I want to use a PMU protocol C37.118. And maybe for fast actions, I want to use IEC 60850 goose messages via my wide area network, so to be very fast in the actions. The next thing is also you should place, from our point of view, research and development topics on this roadmap. So what are the problems, how to tackle the problems, also define some research projects and pilots. And maybe with vendors, you can say, okay, I need tailored building blocks, like one sensor must be very special, or one actuator must be very special in my system. So I think this could be also possible. And also you have to think about processes in your company. So you might, to be aligned with all the maintenance process you have, also you have to do trainings for your operators and engineers. So maybe learn from each deployment step you have. And at the last but not least, maybe regulatory considerations can be good. So maybe there are incentives to enable this technology. Maybe there are processes to integrate different entities. Maybe you can incorporate in this WAMPAC system prosumers or virtual power plant communities, which might come up in the future. And also it could be very good if there's a standardized exchange of information between the utilities. So just our ideas from our perspective, from the consulting, how is the way to achieve WAMPAC. And at the end, just to give you some information, what we are doing at the moment, or we are thinking about, is how to test it. So you can use the RTDS testing with these full scheme. You can use maybe all the devices you have, and maybe you are limited in your RTDS equipment, you're limited in the amplifiers. So then you can only test a small scale system, for example. So therefore, we introduced so-called CGuard DDM, Dynamic Digital Mirror, which uses let's say a planning software, the PSS Syncal, for simulations in the study phase if you use it. So you check, okay, is the action working? What problems I might have? This is combined with our CGuard PDP, so our wide area monitoring system, and then you can check the logics with the system without all the hardware, RTDS, and so on, for system stability checks and which action is the right one. You can use a different system, the DDM, so combination of our controllers, PDP software, monitoring, protection, and control software, and PSS Syncal. So on your own desk, you can check is the configuration of the CGuard PDP correct. And so what makes it easy here is you have the same model in the planning software and also in the testing software for your controller and your wide area monitoring and protection system. So the system security can be tested, and this can all be checked if everything is fine in the configuration of the PDP. And at the end, you can also do the factory acceptance test with RTDS. So that is the communication latency perfect? Does it work? And does all the systems or all devices work together? So,
okay, Mr. Christian,
thanks for your attention.
Okay,
this is my last slide.
Okay. Thank you, Mr. Christian from Siemens AG for the interesting presentations. There are so much knowledge that presentations contain. Deep dive into what is wide area monitoring, protection, and control, separated into 3 applications: wide area monitoring, wide area protection, and wide area control. And it also brings the conceptual design of WAMPAC that shows WAMPAC building blocks covering actuators, metering, central equipment, wide area network, and external systems such as SCADA EMS and dynamic line rating. And last but not least is how to implement WAMPAC through roadmap development, infrastructure and architecture to be built, and then network protocols, software and hardware to connect all the functions, R&D for funding new algorithms, company process to set up operational and business process, and finally regulatory considerations on integrating different entities. Okay, I guess it's time for the first Q&A sessions. We are now going to take questions from Q&A box on Zoom and live chat on YouTube. So let's invite Mr. Sankara and Mr. Christian to switch on the camera. Okay. And as a reminder, the webinar participants can still submit questions through the Q&A box on Zoom and live chat on YouTube. So, okay, let's see the first question. Still waiting from the organizing committee. Okay, hold on a minute. Okay, the first question from Ricky Komarudin from ITB. How to set mode of islanding protection scheme in smart grid systems? The question is for Mr. Sankara. Can you answer the question?
Yes. Is that an asking for an example, or is that true? Can you repeat the question? Is that for example of islanding schemes, or how do we implement?
He's asking how to set mode of islanding protection scheme in a smart grid system.
How to set, Mark?
How to set mode, the mode of islanding protection.
Oh yeah, okay. So I think again with the monitoring of again the active power as well as the reactive power, and based on the cumulative monitoring of the power at the generation side of it, as well as with what is actually connected with the grid side of it, we can have the schemes which are again either based on event based or response based. Now, response based in this wherein it is involving islanding, I would say still event based should help, but in some cases we may also try and use the response based, which is basically looking into the rate of change of frequency, the rate of change of power, and so on, considering within the tactic tables of the SIP schemes, and hence then activate the islanding schemes. Now, one part is once an event happened and then action taking. The other one is actually based on the rate of change of the units happening, which is in this case frequency or power or whatever, and then to activate these before even an eventuality happens for the islanding. So SIPs or the WAMPAC based schemes are very well paced to actually achieve this kind of islanding schemes. I think this summarizes the brief answer to this question.
Okay, thank you for the response, Mr. Sankara. And the second question is from Ayesha. She doesn't name the organizations, but the question is, any WAMPS applications by GE ever installed, trial, and operated in TLN facilities? Over to you, Mr. Sankara.
Yes, I think I replied back. I would read the answer what I have just typed in there. Yes, GE has WAMP solutions both in IGAT, Thailand, and just a few examples, as well as Electronaut system in the Australia. These are few examples, and one of my colleagues has also complimented my answer by saying that we have also been participating in the PLN P2B beauty contest in the recent past. So these are few examples for GE WAMPs participating in some of the either the trial examples or real commercial systems put into usage in the region.
Okay, thank you, Mr. Sankara. The next question is for Mr. Christians. Based on your experience, what are the big challenges that you frequently face when you want to implement a WAMPAC? Please, Mr. Christian.
So I think the most challenging is to define all these building blocks and then and so on. And I think this is one thing and the most thing I have in mind at the moment for installations and deployment in the field.
Okay, so how do you test it in the real environment?
In the real environment, I think the colleagues tested it with different synchronized Omicron devices and checked the inputs for the scheme and also checked the outputs in different. I think we implemented one scheme with in 3 different substations, and they tested it. I think like in this way.
Okay, thank you. The next question is for Mr. Sankara. from Mr. Agus Yogianto from IT PLN. How we decide for the level of the scheme for protection defense related with system capacity? Do you get the questions?
Sorry, can you
how we
dissect
decide
it a bit?
Okay, how we decide for the level of scheme for protections defense related with system capacity?
Yep.
So how we decide? How do you decide to the level of scheme for protection defense related with the system capacity? Maybe for 100 megawatt or 200 megawatt system.
Okay, got it. Okay, yes, okay. So it depends what the study outcomes are leading to. If the study outcomes are leading to that you need to perform load shedding, or if the study outcomes are leading to actually we need to perform generator dropping because of you can't still control the oscillations and so on. So there are two phases now. Once you understood that, okay, I need to shed 100 megawatts, just an example. Once we understand this, and then across, is it across multiple sites or single site? So that then comes into fore. And once we understand, okay, it's going to be 100 megawatts. Again, I'm just taking some examples off the head. 100 megawatts again across 10 sites. Just complicate it. We like complication, right? So 100 megawatts across 10 sites. How do we actually shed them to achieve, to maintain the integrity of the connected network? And so once we know that, then we will consider that within the tactic table of what needs to be done, when it needs to be done, at what contingency at n-1. Now, in terms of the devices, there is a central controller. As far as our solution goes, all we need is one central controller to take these actions, and then we can build up the redundancy on that, depending on how severe, and then we can build on the redundancy. So to shed 100 megawatts of load, just as an example, so all we need is a controller, and then you can build the redundancy parts to that, and the measurement components also needs to be integrated. So the solution component for such a system would be A, the central controller, B, the measurement system. Actually, the measurement system has to come front, and you may need phasor measurement units depending on what is it that we are trying to achieve because of the PMUs. Is it going to be leading to detection of small signal oscillations? Because with all these renewables now also integrated, we need to do that, perform that as well. So is it adding some value, or is it also adding some value in terms of, do I need phasor-based algorithms? Actually, is it going to provide phasor-based inputs so that those algorithms can get triggered? They need this phasor-based. So you may or may not need PMU. So that is the second part, but you still need the measurement units via 103. And then you also need the switches to complete this whole scheme. I hope that answers.
Okay, thank you, Mr. Sankara. The next question is for Mr. Christians. Could you please elaborate more on the limitations caused by RTDS?
Okay, some limitations by the RTDS. It depends on the laboratory you have. It depends on the hardware scheme. So you can implement maybe the full scheme if you have all the racks you need and all the processors you need and all the amplifiers you need. Maybe if you want to test a large scheme with let's say 100 PMUs and so on, then maybe you have to connect all these PMUs to the RTDS, and if your laboratory cannot cope with this, then you have to reduce the number, and maybe you cannot test the full scheme or just some, let's say, sub schemes in a lower layer and not the full scheme. And this could be a reason why you have to simplify something in an RTDS test.
Okay, thank you. And next question is for Mr. Sankara, do you have a comparison between how much do we spend money on reinforcing the infrastructure than implementing WAMPs regarding the increasing float or generation capacity?
Okay, so
because you mentioned in the second slide, yeah, in your presentation, yeah. Okay.
Yeah. So I need to clearly ask: is it WAMPs or WAMPAC? So just the monitoring part of it, or just but also to cover the monitoring and the protection and control part of it. So I would think this, because this is WAMPAC session, I think the question encompasses not only monitoring but also the protection and control part.
Yeah, I think it's
yes,
also included WAMPAC. Yeah. Okay.
Yes. So in which case, I think if you had to provide those again on a small scale level, not on a wider scale level, something around 500 to a million would be the kind of a ballpark figure, just for a which adds to include monitoring and some of those monitoring functionalities as part of it, and the protection and control scheme for maybe a bigger island, or that would be the kind of. So I think it was asking about the estimate, right? The question is about what is the estimate.
Yeah, the estimate. Maybe in a percent, maybe. So yeah. It depends.
Okay. What is it needed? It depends. So if the scheme required is a simple scheme, then if the scheme required is to employ redundancy, if the scheme employed is requiring firewalls more and so on, I think so. Then it adds to that cost.
Okay. Okay. Thank you.
Thank you.
And next question is for Mr. Christian. The question is from Royan Pertamina. Mr. Christian, is there any vulnerability of synchroprocessor-based MPEG applications to time synchronization spoofing? Please answer the question.
Yes, I think it's a very, very technical question about, I think, the signals from the GPS, can they be spoofed and so on. The problem is I'm not from the product side at the moment, so I cannot quite good answer this question. If there's any scheme or security things inside the device, maybe an idea from my side could be if you can introduce maybe the GPS location of this PMU into the system, and then check is it still correct, or does it changed or something like this. This is an idea from my side. Maybe Sankara, you have also.
Maybe Mr. Sankara, can you help to answer the questions?
Well, I can't as well pretend, but I'm a power systems, but basically also from power systems. What was the question? Can that be?
This is about time synchronization spoofing for the synchroprocessor-based WAMPAC. So it is any possibilities that we can spoof the time synchronization?
Well, I would have to pass this question actually. Again,
okay.
Given my background in power systems, but not on products exactly on the
Okay. Thank you, Mr. Sankara.
Yep.
Okay, so I think we have run out of the time, yeah. So we are now having a break about 10 minutes to enjoy our sponsors' videos, and then we will be back immediately afterwards. Okay, please, organizing committee.
Tide strongly believes the importance of environment protection and energy efficiency in order to achieve a sustainable future for mankind. Thus, our technological commitment will foster mutual betterment of our allied companies, customers, shareholders, and employees. Tide pledges to always hold our management philosophy and values at heart. Until now, the meter readers have had to do manual meter reading. This existing manual process is time and money consuming work. This makes it hard for us to detect blackout and manage energy demands. And it makes us hard to manage loss during transmission and distribution. As a result, this existing manual process makes grid unsmarter. But TOT's end-to-end AMI solutions will connect the user with utility companies. TOT's intelligent AMI solutions will solve many problems from the existing manual process. We can reduce time and money spent metering manually. We can manage blackout and loss during distribution. We can do demand response, TOU. Finally, we can make grid smarter. AMI service. Meter reading information of household is call-cited by modem and DCU. There are two types of smart meter, internal and external. Smart meter sends metering data to modem via serial communication. Modem sends metering data to DCU via PLC communication. DCU sends metering data to server via fiber optic and cellular network. On-time monitoring and detection of electrical loss. TOU, time of USC flexible tariffs. Connectivity to electric vehicle charging system. Connection of renewable energy and battery with bidirectional metering. Reliable collection rate improving monitoring of power quality. Making grid smarter and more efficient. A hidden champion in the energy IoT solution industry. Tide.
know where the light comes from? Tonight, I'm going to tell you a story about the people who keep the lights turned on all around the world. One of the most important things in our lives is electricity. It's invisible, but it heats our home, lights your school, and powers the train that takes your parents to work every day. For your light to work, you need electricity. This electricity travels a long way to get to you. Imagine a massive spiderweb that covers the city and the whole country. Electricity travels through the spiderweb to turn on your bedside light. Adults call the web the electrical grid. It's the biggest machine ever built. It's what connects and powers all the other machines. First, we collect the electrons that come from nature or from big factories that make electrical energy from wind, water, sun, coal, or gas. Then we transform and transport these electrons through the machine. A tough job. We constantly reshape this energy to fit the journey it will take to reach its destination. And then we control the machine. We make sure the electrons find the best path through the spiderweb and deliver it safely to every corner of the planet. The need to keep electricity flowing never ends. There is so much work to do to keep the electrons flowing all over the world to light the homes of little children just like you. That's why I'm so proud of the work I do every day to help make all this happen.
Okay, let's start the second session. I hope you enjoy watching interesting videos from our sponsors. I would like to do a few housekeeping here. The attendees or participants have the opportunity to submit text questions to today's presenters by typing your questions into Q&A box on Zoom or via live chat on YouTube at any time during the presentations. Please mention your name, organizations, and to whom the questions are posted. We will then collect the questions and address them during our Q&A sessions. So let's move forward to our next agenda, which is presentations from Mr. Suroso Isnandar from PT PLN Persero with the topic of overview of WAMPAC in Jamali Power Systems. But before the presentation begins, I'm very pleased to inform you a brief biography of Mr. Suroso Isnandar. He received a bachelor's degree from Institut Teknologi Bandung and holds master's degree in University of Aberdeen, Scotland, UK. And he is currently working as a general manager for Java, Madura, and Bali Load Dispatch Center at PT PLN Persero. And without further ado, I would like to welcome Mr. Suroso to deliver the presentations overview of WAMPAC in Jamali Power Systems. So please, Mr. Suroso Isnandar, you have 15 minutes and the Zoom is yours.
Thank you, Pak Tri, as the moderator, for the opportunity given to me. Good afternoon, ladies and gentlemen. Distinguished speaker, allow me to presenting the overview of a wide area monitoring system application in Java Bali grid. We call it Jamali, which is stands from Java, Madura, and Bali, because this Java grid connecting 3 islands. My presentation will be organized using these 4 topics, basically the system overview and looking at the WAMPs in Jamali Power System, and then we are looking at the roadmap of WAMPAC in the future and summary. Because at the moment, the Java, Madura, Bali grid state from the using of the WAMPAC actually is in a very early steps, very early pilot project. We don't have any application on the wide scale yet. So, ladies and gentlemen, the Jamali Power System has a peak load of 27 gigawatt, which is reached on last June, 8th of June at 6 p.m. with installed capacity of 38.5 gigawatt. And our fleet mostly come from the coal-fired units, accounted for 68% of the energy mix, and then followed by gas, which is consists of LNG and also CNG, and then followed by hydro and geothermal. And as a backbone, we have a 500 kV grid connecting a whole Java island. which from end to end probably within distance of 1,200 kilometers. We have a load profile something like this. We have a 2 peak, which is during the day, afternoon time at 1 p.m. and also during evening time around 6 to 7 p.m. If we are looking at the wide area monitoring system overview, is basically, to put it simply, that the wide area monitoring system rely on using application of synchro phaser or phase monitoring units, which basically giving us more sampling time. I think within one cycle, we will take a sample. So if using 50 Hz, then we are talking about 50 sampling during a minute. And basically putting the PMU scatter all over the place. System Java Madura Bali system at the moment consists of 252 generating units and also around 600 substation. But from those 600 substation, at the moment we only install in 38 locations. So a lot less than what we needed. So that's why we're calling that they're still on the pilot project phase and not on the full scale implementation yet. Of course, there are some benefits we'll get from the WAMPS application here. For example, we will have the more GPS time accuracy using nanosecond scale and also angle accuracy. This is probably less than 0.05%. And if we are looking at the way the data are acquired, so it will provide us with a high precision. By that way, then we'll have more knowledge, deep knowledge into our system dynamics. In the Indonesian grid code, number 20, year 2020, the regulator or the mandated all system operator must install the WAMPS equipment in the substation or in the power plant, which is in connecting code 4.7. And also, they have mandated that the special telecommunication facilities for the operation technology functions, such as WAMPS and PMU, must be spirited from the SCADA network and also from IT function, which is stipulated under the connection code 4.12. And also from the appendix CCA 1, 3, 2, 3, and 10, this PMU application should really support the long-term WAMPAC vision application into the system and can be accessed remotely by system operator and also integrated with WAMP server installed in the control center. So what we have at the moment is the configuration of the existing WAMPS network where the PMU is connected, which is scattered all over in the substation. At the moment we have 38 locations, and also we're trying to utilize the PMU function from the DFR or disturbance fault recorder. We have around 120 or more, so we are talking about 160 points. Then they will be connected through the PLN wide area network, which is spirited from our SCADA network in configuration with the cyber security. And also we have the server, which is using the redundant principle on the Java control center together all of the information and data we taken from the grid. So the configuration of existing WAMP server consists of 2 servers. At the moment, we have the Dell PowerEdge R720, and also we have the redundant server with spirit storage. And in the future, we are adding procuring more additional server with 24-bit class. So we will have a capability for connecting more PMU at the moment. And the existing one using the SEL brand with the Synchro Wave application as the interface for the operator to look at into the system situation. And the existing PMU configuration where the current and also the voltage reading are taken from the field, from the substation, from the current transformer, and also from the potential transformer. and through the PMU, Pressure Measurement Unit, will be send it into our server on the Java Control Center. And on top of this, we also access the PMU function within the TFR, Disturbance Fault Recording Relay, based on the standard of IEEE C 37118, which is actually IEEE standard for synchrophasor on the power system. At the moment, from those 38 PMU and additional 120 PMU function in the TFR, we envision the utilization of WAMPs into three big functions. The first one is for the analysis and evaluation to capture the characteristic, for example, the inertia of the system and also the stability of the system on the system stiffness. And also, we are using all this data to do the post-mortem analysis after fault or after incident occur to investigate the sequence of event of a big disturbance in the system. For example, the one we provide here is actually a real capture from the previous disturbance in the system. And also, of course, to increase the situational awareness, to access the real-time dynamic monitoring that will assist the dispatcher to monitor power system dynamics and react proportionally in order to keep the system in balance. And from here, we can see the example of the WAMP user interface, either from the phasor measurement, the frequency measurement at different point of the system, also voltage measurement and also power measurement. For example, here we have the substation Banyuwangi, which is on the eastern tip of the island. We compare it into the substation in Bekasi or in Sentul, which is on the western tip of the island, and we can see the difference. And also we compare it, the voltage and power measurement within a particular substation. We're trying to look at the detail of it. In the future plan, we will develop a new control center, and this is the snapshot of our picture from the existing control center. In 2023, we are hoping that we will build a new control center, and in this new control center, we are expecting that the ones can be developed and integrated into the new control center, and of course, hopefully, from that stage, then we can carry on using the WAMPAC scheme in order to improve the function of the system. PMU will correct the state estimator calculation at the moment, and also to be integrated with the SCADA dynamic security assessment in order to improve the situational awareness of the system. So looking at the existing configuration, we are looking at the way ahead in order to deploy the WAMPAC into the system. Based on the philosophy, looking at that WAMPAC should be a system that capable of monitoring the status of the power system in real time, that enable to execute control measure and automatic protection in order to restore the power system network to the stable condition or prevent further deterioration when the system is in an emergency condition. Of course, on the time, the dispatcher have to keep the system stable and secure, but on unfortunate event, if the system move into the alert position, we have to take a preventive measure. And also, if there is some more disturbance and which is bring the system into emergency, then we will have the automatic control measure using by WAMPAC in order to bring back into the stable system, or even on the extreme emergency, it will help the manual restoration into the stability of the system. If we are looking at the range of influence of the impact of the disturbance from the wide into the narrow, and if we are looking at the time scale of control from the several milliseconds into 10 minutes, we have a lot of disturbance that we have to look for. For example, the wide area frequency stability, which normally could happen within seconds and influence a whole system. Also, the cascading phenomena or other kind of transient stability like rotor angle stability, or maybe a frequency stability into islanding system, or in the narrow impact of the disturbance, we have to look at the voltage stability and also the overload of the system. We expecting that the WAMPAC can help us in order to anticipate this kind of contingencies and react accordingly. Of course, the benefit of WAMPAC is very wide. We have wide area phase angular and port flow monitoring, and also we could have the wide area frequency monitoring, wide area voltage monitoring, or we can look at into the inter-area oscillation monitoring. In particular case, we're looking at the power system restoration scheme or improve the state estimation, and also looking at the dynamic rating of overhead transmission line when the system is operated and pushed into the border, and also the intelligent control islanding or adaptive under frequency load setting. So at the moment, we are preparing to build the new area advanced control center. In parallel, developing the WAMS and also the advanced defense scheme to mitigate several contingency events, and hopefully this will put a puzzle together into the WAMPAC scheme for the Java Madura Bali system. And this is the roadmap of what we are going to achieve. We are expecting that in 2026 we will have 100% WAMPAC scheme implemented in Jamali system. Of course, if we are looking at the existing state at the moment in 2021, we have to do some upgrade of storage server WAMs, and then to add into more PMU into the system, and also utilizing PMU function of the DFR in order to complement and implement our existing equipment. The WAM server at the moment, we have two, using the hardware Dell and the software SEL, and the PMU SEL, which is only a 38 sets from around 600 subscriptions we have. And next year, we are looking at to upgrading the WAM server and also the integration of PMU based on PFR. And the work will carry on until 2023, and where we are starting looking at the integration in large scale. We are looking at more and more substance has been covered by PMU. And then in 2024, where we will have our new advanced control center, we are hoping that the expansion of PMU can be integrated into our new control center. And by that year, we are adding more WAMPAC scheme for implementation and trial, and also connecting to advanced defense scheme or SCPS or remedial action scheme in other terms. So by 2024, we are hoping that we will have a 60% WAMPAC in progress. And then this work will continue in 2025, upgrading the WAMS and WAMPAC server, and also the expansion of WAMPAC and advanced defense scheme integration. And hopefully by 2026, we have all the substation has been covered, and we will have a complete set of the WAMPAC system into Java Madura Bali. And this is something we are planning for in the next coming years, and hopefully we can have this happening very soon. So in summary, that in the Jamali power system, we are still on the very early stage of implementing WAMPAC, but we have been trial doing the pilot project using the wide area monitoring system. And at the moment, we use it limitedly for the real-time system dynamic monitoring, and also looking at the system analysis and also evaluation, and also looking at the post-fault investigation if there is some incident happen or disturbance happen in the system. And based on the roadmap, in order to implement WAMPAC in Jamali power system in the future, at the moment we starting step by step by increasing the capability of existing WAM server, and also trying to add in more PMU into more substation, and also integrating the wide area system once with our new would-be advanced control system, control center, and also adaptive defense scheme. Although from the limited application of PMU and WAMS that we have at the moment, we already have some several lessons learned, which is very important as well, in order to upgrade our knowledge, upgrade our infrastructure to move into the WAMS. We have recognized that several critical vulnerability of the system dynamic need to be addressed and need to be mitigated through the application of WAMPAC system. So in this opportunity, this is what we can share with the audience regarding the early application of wide area monitoring system into Java, Madura, Bali. And after this, any question will be gladly welcome, and should we discuss any further, then I will be happy to answer it. So thank you very much for the time. I will give it back to the moderator, Pak Tri. The time I'm giving back to you. Thank you.
Thank you, Mr. Suroso, for the comprehensive presentations. There are a lot of work and experience that I've seen that has been done in Java, Madura, Bali, Java, Madura, Bali Load Dispatch Center. And then it has been shown in the presentations, lots of the insight. I would like to mention some of them. PLN Java, Madura, Bali, our system already equipped with a wide area monitoring system, and it's been utilized for real-time system dynamic monitoring, system analysis and evaluations, and post-mortem analysis to get the sequence or big disturbance data from the systems. So right now, PLN Java Madura Bali advancing to integrate the WAMS with the new control centers targeted in 2023 and still in progress. So based on their roadmap, on 2026, they will implement a WAMPAC and adaptive defense systems, or ADS, fully 100%. Again, as a reminder, the attendees or participants have the opportunity to submit text questions to today's presenters by typing your questions into a Q&A box on Zoom or via live chat on YouTube at any time during the presentations. Please mention your name, organizations, and to whom the questions are posted. We will then collect the questions and address them during our Q&A sessions. So we are going to move to our next agenda, which is presentations from Pak Dede Subakti from California, CAISO, on WAMPAC in California grid system. But before the presentation begins, allow us to read a brief biography of Pak Dede. Pak Dede received a master's degree in Business Administration from the University of Minnesota and a master's degree in Electrical Engineering from Iowa State University with an emphasis in power systems. So he received his bachelor's degree in Electrical Engineering from Iowa State University. For now, Pak Dede Subakti currently serves as Vice President of System Operations in CAISO. He is responsible for all aspects of system operations from bid to bill. This includes new resource implementation process, operational readiness, day-to-day control room operations, all the way to settlement and dispute process. He is licensed professional engineer in Minnesota and certified North American Electric Reliability Corporation system operator. And without further ado, I would like to welcome Pak Dede Subakti to deliver a presentation on implementation of synchroprocessor technology at CAISO. So, Pak Dede, the Zoom is yours, 15 minutes.
Thank you, Patri. Just sound check. Can you hear me okay?
Yep, we can hear you clearly. Okay.
So first of all, thank you very much for the times and the sharings with that you all have. Today, when we want to talk about the implementations of WAMS and WAMPAC, it's such a big item. So I thought that I'd like to focus a little bit about the development of how we use the PMU, which is a synchrophaser technology in California ISO. And then I really enjoy actually what Dr. Christians was talking about, the fact that in everything that we do, you should really take a look at it into three different items, right? There is the wide area monitoring portions where you are using the normal SCADA monitoring, you're using the PMU monitoring, and you're using all the monitoring that you have in there. And then you have your protections portions, that is the normal protection. Then you evolve that to more kind of like a remedial action scheme or special protection scheme, or you just have heard from Pak Suroso that you could have adaptive defense schemes. And then, everything that you have in there, it would end up, kind of developing by itself and maturing by itself. And you let each and every one of them develop by itself. So let me talk a little bit about California ISO first, and then I'll share a little bit about how it's actually evolving within California ISOs and within North America for all those three items that is in there. And then we'll focus on that portion. So anyway, I'm just a little bit of introduction about California ISOs and what we call the Reliability Coordinator of the West, which is DRC West. When you think about California ISO has multiple different functions within North America. California ISO is the reliability coordinator for 80% of the Western interconnection. The Western interconnection is a pretty large interconnection, pretty large, big grid in there. But the California ISOs, you always hear about California because the name itself has a California, and it's actually manage and balance the transmissions and the generations within California, which is actually about 80% of California. I'm showing some of the statistics here on the bottom right-hand corner here on California, because California is pretty forward and upfront with regards to our renewable. So you would see that we have a large amount of capacity of solar, 14,000 megawatt of solar, 7,000 megawatt of wind, and out of that 14,000, we've actually achieved 13,000 megawatt of solar peak production, and so on and so forth. So you saw a lot of this is a large number. If you were to compare, I think California is probably a little like the Java Bali systems, a little bit more. Probably our peak demand is about 50,000 megawatts of load that we have. A while ago, actually, in 2006, we get closer to 50,000 again on 2017 that is in there. Now, like I mentioned early on, maybe I should go back here. When I mentioned early on, you've heard from Sankara about the fact that we have a number of what we call a remedial action scheme in this North America. So if he went through it really quick, and we have a bunch of GEs N60, for example, all over PG&E area, Pacific Gas and Electric area, and there we have a lot of remedial action scheme, right? So those are all the remedial action scheme that has been in there then, and that remedial action schemes is for the most part, a lot of those are private SCADA system, private measurement system that go through a goose system like what he was mentioning, and it all goes to the action that is taken that is in there. So we have a lot of those remedial action scheme that is part in there, and it has grown by itself, just like what Dr. Christian was talking about. The remedial action scheme grown by itself, the monitoring portion is grown by itself. So what I want to talk a little bit about this is actually how the other side of this, which is the synchrophaser, which is the PMU data that actually also grow by itself. It was growing in separately but in parallel together, right? So the synchrophaser data is actually, again, it's basically growing by itself. We have multiple utilities. So unlike in Indonesia where you just have PLN, in North America we have many utilities in there. So I'm just using an example here, like BPA, which is Bonneville Power Administration, PG&E, which is Pacific Gas and Electric, or SCE, Southern California Edison. You heard about SRP from Sankara, which is Salt River Project. So each one of these people are their own utilities. But one thing that we do is we talked about the fact that we have to be able to share that data. We have to be able to pass this data back and forth back to California ISO, because California ISO is the reliability coordinator. We manage and coordinate all these stuffs with us. So the way that it's actually being done right now, all this data and everything is being put into what we call the phaser data concentrator or phaser data gateway, and it's actually being put into concentrator in their site, and then we have a network, and that network is actually is an AT&T network. Is an AT&T network that we created specifically for this PMU data. We call it the WIS, which is Western Interconnections data, basically for synchrophaser, and we put that into our control center, because we have our control centers in one place, and we have another control center. They both active. So then this synchrophasers data get put into both control centers, and we have a bunch of other stuff, and then we have the storage, and then as you can see it, that we store it in the SQL server, we store it in the Pi server, and the data is there for us for further utilization. So again, this is one side of the remedial action schemes growing by itself, and this PMU data growing by itself, and they're maturing. And when it was maturing, it was trying to get into the grips of, how do we actually going to use that? There's a lot of discussion is what are you actually going to use this PMU data? Because the PMU data, synchrophaser data is kind of sort of people was talking about the fact that this is a solution looking for a problem. It's very funny because people would say that, hey, we have all this data now, what do we do with this data? So we actually struggle with it quite a bit, honestly, trying to figure out what do we want to use this PMU data for. And I'll talk a little bit more about what we've been doing in the past. But what really pushed this into fruition is the fact that we actually have a change of the North American NERC. It stands for North American Reliability Corporations, and it's actually just kind of like a grid code. And the grid code was very specific for the Western interconnections, and the grid code was very specific and basically says reliability coordinators such as California ISO, you have to implement a process to see inter-area oscillations, and basically says you got to be able to make sure that the system is reliable, and you have to be able to find out the inter-area oscillation. So we get into a point where it basically says the grid code says so. The grid code says that you have to be able to do this, and this is an enforceable grid code that if you don't do it, you could get penalized up to $1 million a day. So this is the one that's actually really pushing the fact that, okay, now we have a bunch of PMU, now we have a standard and the grid code that says you have to do it, let's do it. So what we've done then, we created an inter-area oscillation detections, and we take data from all the phaser measurements, and what we learned is we actually do not need all of this data. I think Suroso was talking about the fact that they have 38 in there, and if you put that 38 in the right place, you probably could utilize this pretty good too. So we actually realized this, that to figure out of inter-area oscillations, first of all, we need to know where is that oscillation, and we have a predefined mode that we are monitoring. There's a north-south A mode, north-south B mode, east-west mode, and what we call the British Columbia mode and the Montana mode. So we have 5 modes, and each of these modes, based on the analysis, based on historical experience, we know what's the frequency, what is the mode, what is the frequency that we have for this inter-area oscillation. So what we end up doing is basically we specifically utilize a predefined angle pairs to monitor the energy and the damping of the 5 modes. So we really don't need a lot of PMU because you actually just have a pre-selected place where you want to put this PMU. So that's one of the lessons that we had, is that you don't really need all of them. You just have to figure out where do you want to put them. So then you work with the operators, you get all this stuff, you get all this fancy stuff on the inter-area oscillation. So I'm going to just quickly do this. So we figured out that the inter-area oscillation is good. Then typical damping of the natural modes can be increased by, damping can be increased by decreasing the megawatt flow, reducing outflow for critical generator, and all those other stuff that's going on in there. Now, before we actually get into this inter-area oscillations, and I only have 4 more minutes here, probably 5. Before we actually get into this inter-area oscillation, which is a big thing, right? This is the big PMU stuff. We actually walk through it. Again, going back to what Dr. Christian was talking about, that you actually have to let this develop naturally. So for us, we basically let the PMU and the utilization PMU is actually for monitoring and control, and it's actually developing naturally. The first thing that we do was actually doing a phase angle monitoring for sync check in the long transmission line. So just like in Java, in California, we have a lot of 500 kV long lines. It's very similar. So in that 500 kV long line, what could happen is if you have a contingency on that line trip, you have to close back the line in. But before you close back the line in, you have to make sure that that line, when you close it in, it had to be within your synchro phase, within your sync check, right? So it's a very easy, simple application that the transmission operators are very used to. They just know that when the line is open, they have to close it. They have to have a sync check. They have to make sure that the delta angle, which is the voltage angles in there, should be close enough. So for us, it's actually just very simple. Okay, you could actually calculate an angle using a PMU, so you know that whether or not this transmission line can be closed in or not by using a PMU. And if the angle is too wide, you move the generation. Once the angle is close enough, then you can close it. So a very simple application of PMU where you allow the integration of the utilization of PMU in the normal manual control of a human being, and that gets operator to feel comfortable and feel used to this. The other one is talking about the phase angle monitoring for stability limit. Just like Pak Suroso was talking about, you could actually measure one end of the East Java and one end to the West Java. When you export power from the East Java to the West Java, you can see the angle between those two substations. Same here, Northern California and Southern California. You send power from Northern California, you receive it in Southern California. You could measure it, instead of measuring it in megawatt, you measure it in the angle. So you could do the same thing. It's this, because Java Bali is very similar to California. You have a 4,000 megawatt limitation or 3,000 megawatt limitation of power transfer. That's normally measured in megawatt. You could actually put that in the angle monitoring. Now, I have 2 more minutes left here. I want to talk about a little bit about force oscillation. Force oscillation is something that's actually really unique for that we've just been learning more and more. For oscillations that we have is that this is an oscillation that is actually a little bit different than inter-area oscillation, and this is that we've been monitoring it for different bands, but that is basically a situation where a particular unit can actually have a control issue or whatever, and then they started a force oscillation in the system, and that force oscillations could create a wide area oscillations because of the resonance that we have in there. So this is one thing that we start monitoring, we start learning, so we start growing again. Just like the whole concept here is just learn something, get accustomed to it, and then you grow your technology implementations in there. So that's all I have. I think I'm almost done here. Oh, one more thing, that because I think Pastor also talks about how the implementation of advanced control centers where you could have a real-time transient stability analysis like TSAT, VSAT, and all those other stuff. One of the biggest important thing is to actually have the model validation. We could actually use the PMU data. The engineers, the operations planning engineers, the planning engineers can actually can use the PMU data and validate the model that you use in state estimation, the model that you use for real-time transient stability, and all those good stuff. So these are just a number of items, but I think at the end of the day, what I'm trying to say is that I cannot agree more with what have been said by Sankara and Dr. Christian, is that the fact that if you have wide area measurements and you let it develop, you have your RAS, your special protection scheme, you let it develop, you get your portions in there, and then you make that everything's working by itself. And then you put it together so that your operators actually could actually adapt to it, so that, because at the end of the day, technology is good, but your operators need to be able to actually absorb it and actually be part of your cultures in there. So that's all I have, and we'll put it back to Pak Tri. Thank you so much.
Okay, thank you, Pak Dede, for the interesting presentations. Allow me to summarize the presentations, which describes how synchroprocessor data is being collected from pressure data concentrator and shared to two control center of KAISO and being utilized in different applications. There are 5 modes being monitored in inter-area oscillations: North-South mode A, North-South mode B, East-West mode A, British Columbia mode, and Montana mode. And then operators will receive alarm for sustained low damping under 3%, and they need to take actions to increase damping with the operational guidance, which are validated through model-based studies using small signal stability analysis. And then the synchroprocessor data is being utilized for other applications, such as phase angle monitoring for sync check, and then phase angle monitoring for stability limits, force isolations, and model validations. Okay, nice presentations, Pak Dede. It's time for our second Q&A sessions. So we are now going to take questions from Q&A box on Zoom and live chat on YouTube. Let's invite Pak Suroso and Pak Dede to switch on the camera. And also, as a reminder, the webinar participant can still submit questions through the Q&A box and Zoom and live chat on YouTube. Please also fill in the present form posted on chat room and live chat on YouTube. You will receive an e-certificate for this webinar participations via email for 7 working days at the latest. And then the webinar presentations material will also be sent to your email. So, okay, so our first question is for Mr. Suroso. Pak Suroso, would you elaborate more on the challenge that PLN have to face on implementing wide area monitoring systems and what PLN will or should do to overcome those challenges? Please, Pak Suroso.
Thank you for the questions. So basically, whenever we apply a new technology, we have to look at 3 aspects. The first one is the technical system. Second one is the people system, and the third one is the management infrastructure. I think on the technical system, every engineering problem there is engineering solution. Also on the management infrastructure, we can put in all the SOP and every procedure that we can address into that specific introduction of technology. However, on the people system is very important here, because as Pak Dede also put it previously, using the 38 PMU, we should be able to cover a lot of things in the Java Bali grid. And yet at the moment, we are still wondering what we should put into our scheme first. So that means we have to again look at our network, again looking at the vulnerability of the network and which one we need to address. There are a lot of vulnerability for existing into the Java Bali grid. For example, the amount of transfer from Eastern into Western. And also we have to look for the voltage stability on the load center, in this case in Jakarta, because in certain occasion, because of the high transfer from the Eastern into Western region, and then there's a lack of reactive power on the Western side, and therefore the voltage stability on the Western side become a problem. And also there are some big transfer power from the Western block of power plant on the Western tip into the load center in Jakarta. And there is also some vulnerability on the long interconnector on the south side of the Java Island. So defining the scheme, looking at what we are trying to address with this technology, and take the main benefit of it. That, in my view, is the biggest challenge and difficulties in implementing and production this WAMPAC technology. The technology itself, now already out of the self technology, we have a lot of options, we have a lot of providers that can be compared into our specific needs. But again, defining what we are going to do in the system is much more important. So I hope this answered the question, Patri. Thank you.
Okay, thank you, Pak Suroso. Maybe I will continue the questions regarding the people issues that you all mentioned before. Do you have a sufficient person or human resources to take over or carry the WAMPAC implementations for the next 20 or for the next 3 or 5 years on 2026?
Okay, thank you for the question. At the moment, we are planning to build a new control center, replacing the existing obsolete control center. And together with that, we will organize the way we manage the control center. At the moment, we have a modular approach where we have Java Bali Control Center in Jakarta, and then we have 5 regional control center, which running into the specific area of the system. But this modular configuration is, from the redundancy aspect, is very good. But from the manpower and other optimization of resources, may be quite challenging. And in the future, we will consolidate those 6 control center into 2 locations. One is the main control center, and the second one is the redundancy control center. And alongside with that, we will prepare the WAMPAC application, which hopefully can be integrated into the system. In that case, we are preparing all those, not only equipment, also from the human resources. We have a lot of young talent and engineers, and we are also working with consultants and universities for doing the study and conducting what is the necessary scheme we need to put in place at the moment. At the moment, we already have some advanced adaptive defense scheme in place. For example, Muara Karang or North Jakarta power plant complex. We have a specific SCPS there, or adaptive defense scheme. And also we have the adaptive defense scheme applied for the managing transfer into Bali Island from the eastern side of Java Island. We put adaptive defense scheme open there. And also we have one adaptive defense scheme running in Central Java on the south side, where there is, because of the locational advantage, the power plant in Cilacap have to be managed such way, so if there is anything happen over there, does not compromise the integrity of the system. And from this scheme we applied, we learn a lot, and we are preparing our team in order to anticipate the full-blown application of WAMPAC by 2026. Thank you, Pak Tri.
Okay, thank you, Pak Suroso. We'll move to Pak Dede. Pak Dede, the question is, based on your experience, what actions does the operator take if they receive alarm from wide area monitoring systems due to the lower damping? As you mentioned in your presentations, that they will take proper actions if they receive the alarm.
Yeah,
Can you explain?
Sure.
Okay.
So the we do have what people would probably call it as the SOP, right? The standard operating procedures, or some people call it an operating guideline or operating procedures and whatnot. So for us, it's the same thing. So what we do is we've done analysis and studies that is done by the operations engineers, the operations planning engineers, and the analysis shows that there's at least 2 or 3 items that are actually pretty simple to do to reduce that inter-area oscillations. The inter-area oscillations that is very common is when you send too much power, or when you send a lot of power from the northern, the northwest, the Pacific Northwest, which is Oregon and Washington down to California. There's a bunch of 500 kV line, and it's actually a long line. And you could have that quarter hertz oscillations, and then you'll get an alarm. And if the alarm is there, what we've studied and what we've analyzed is that there are things like, of course, reducing the power transfers by redispatching unit that would work, but that's normally very expensive. But before people go there, there is actually other items such as putting synchronous condensers. We have a lot of synchronous condensers. The synchronous condensers actually put mass in the system. It's actually have voltage control. It has a lot of other item that you could do in there. So synchronous condensers, SVCs, those are the cheaper options. If they're not online, put it in online. But the more expensive option is when you start redispatching generation out of merit to reduce that power transfer.
Okay, thank you, Pak Dede. So you already have a standard operating procedure for the operators to do the necessarily action, yeah. So we have a next question from Mr. Sankara. From Mr. Sankara to Mr. Suroso and Mr. Dede. Both of you have the same questions. How do you handle the problem of curtailment issues that the developers complain due congestion in the grid due to the renewable integrations apart from regulatory points? Any glimpse onto the technologies that you are considering, specifically based on PMU, based dynamic line ratings and dynamic power ratings? Apologies for the length of the questions. So maybe Pak Dede first can answer the questions.
Oh, I was going to ask Mr. Suroso to answer first.
Ah, okay. So
thank you, Pak Dede.
Suroso,
my answer is very short. Thank you for the question, Pak Sankara. In Java, Bali, we don't have any variable renewable energy integration yet. We are hoping to have our first solar farm 150 megawatt by next year. However, in my previous assignment, this is in Sulawesi Island, Spirit Island from Jamali, we already have 140 megawatt wind farm out of 1,000 megawatt of peak load. And also we have on the northern tip of Sulawesi, 30 megawatt solar farm out of 300 solar farm peak load. So on the South Sulawesi system, where those 140 megawatt wind farm integrate into the system, we do have issues with the grid congestion. However, because this is the new development, then we opt into building the new parallel line. This is incorporated into the PPA, and then from that, this will be recouped. So we don't have any issue yet with the grid integration. However, looking ahead on the Jamali system, at the moment we are receiving more than 6 gigawatt of VRA proposal, and from those grid integration study, we already see some problems regarding the curtailment, especially on the connection issues, especially on the curtailment. So this is still on the study level, Pak Sankara, but I think it is a good question we need to look at, because then we have many choices. Either we build the new line, which like the case in the South Sulawesi, but I don't see this going to be the case in Java, Bali, because we already a crowded area over here. So we have to optimize the existing lines. So we have to looking at the dynamic rating of the existing line. So in this case, actually, I would ask other system operator, especially Pak Dede, if you have an experience on the congestion from the grid because of the integration of a new VRE. Because we see this problem will come into the Java Bali grid, where the new proposal, as far as I understand, will connect it at the point, not only in the weak connection point, but also the congested line. And building the new line, not always the case. So we were looking at this curtailment issues. And what can I answer just now? We just need to look at the dynamic loading of the transmission line. Therefore, we'll need this kind of technology in order to look at the detail. But how the scheme will work is still on the study level, Pak Sankara. So I think Pak Dede can answer very comprehensively. Thank you. That's my response. Thank you for question, Pak Sankara.
Okay, thank you, Pak Suroso. Pak Dede, over to you.
Yeah. So first of all, for all the audience that don't know, Pak Suroso and me is actually, we're very good friends for a long time. That's why we like to tease each other. Anyway, but But yeah, I think as you probably noted that in California ISOs, we currently have about 14,000 megawatt of capacity for solar. And we also have that 7,000 megawatt of capacity of wind. And we get there by using a lot of remedial action scheme, a lot of special protection scheme, right? So this is one of those things that we were talking about, the fact that the need was there and we let it develop. As we grow our renewable, rather than curtailing the renewable because of a transmission overload, for example, or because of a stability issues, rather than we also cannot build transmission line because transmission line is very expensive in California. A lot of it is because of the fact that the cost of land to build that transmission line is very expensive. So a lot of the items that we do in the integration of renewable to avoid for curtailment is actually by the utilizations of the remedial action scheme, or SPS, or AD, adaptive defense schemes that you were talking about. So that we basically, I think that's what we talked about, having the GEN60 or the SEL. I mean, it's all those other stuff. It basically says, if this line were to trip, then you would shed this much generations, and we would put a controller to calculate how much generation needs to be dropped and whatnot. And that's basically that we are having right now. We do have a number of dynamic line rating. The problem that we have with dynamic line rating is because, again, the transmission line in California often is pretty long, and when it actually goes pretty long, it actually goes a lot of different terrain and zigzag and stuff like that, just kind of like being in Java. So it's a little bit challenging. But so most of the solution that we have and able to put a lot of this renewable and avoiding curtailment is utilizing the remedial action scheme, in which case that generation would only get dropped if there is a contingency.
Okay, thank you, Pak Suroso, Pak Dede, for answering the questions. I hope it answered the questions. And next question is to Pak Dede. Can you elaborate more on how do you select where to put PMUs in your power systems? Because you mentioned earlier that Java, Madura, Bali power system has a big number of PMUs. I recall maybe 38, yeah? And then you mentioned that we don't need too much PMU for CAISO. So
Yeah.
Can you elaborate more?
Yeah. So what's kind of interesting about that is that for us, we know that there is an inter-area oscillations, and we also know that inter-area oscillations go from the north to the south, for example, right, or from the east to the west. So it's actually very simple for us, because we know that it's done from the north, from the south. Then you just basically find a good set of big generator place or substation that have a lot of generators that is in there in one area, and you put one or two. Well, we end up putting two in the north, and same thing in the south, where you have a bunch of load or a bunch of generations, and then you put two in there. So for every mode, we just have four. I mean, really, that's all. For every mode, we just literally have four, and then you do the angle pair between the north and the south, and then you calculate the actual damping between those four. So we're monitoring 5, and if each one of them need 4, you could do it with 20. So, and then of course you want to verify that it's actually going to meet what you need. But in most cases, you could do it with very simple. But again, you need to know your system, and I think it's very similar. Like in Java Bali, you already know that the power flows go from east to west, just like we know in California the power flow goes from north to south. So
okay, thank you very much. Maybe this is the last question for Pak Dede. Can you elaborate more on the oscillations due to resonance? Because you mentioned in the last slide, but due to the limited time, and then you go thoroughly and fast change the slides. So maybe so many participants in here maybe want to know more deeply in oscillations due to the resonance.
Yeah, sure. So this is actually kind of an interesting thing. Well, first of all, let me go back, right? So the theory of a small signal analysis, the theory of small signal analysis basically say you have a very low damping. You have 3% damping, 5% damping. You have a very low damping, and the theory of that small signal analysis basically says that if you already have a system that is poorly damped, then any type of perturbation, any type of contingency is just going to make it really bad, right? So that's basically what the theory is. So now, what I have been seeing, or what I have been noticing, is that you could have a poor controller. Let's say that an AVR in a particular unit that is not doing really well, or a PSS that's not doing really well, and it's just it could be just a poor controller that gets stuck, for example. And we've actually seen this where an AVR, automatic voltage regulator, actually just gets stuck in the up mode or the down mode. It just gets stuck in the particular power plant. And if that controller in that localized area start having that oscillation, which we call a force oscillation, it start oscillating, and at that same time you actually have a low damping to begin with in your inter-area mode, that force oscillations that was happening in the local area could perturb, or could actually then create that resonance and have that strong participations to the other sides of the inter-area. So now your inter-area oscillation that started with low damping to begin with, now you can actually get see that that energy of that inter-area also, and then the damping becomes really bad. Then you getting a bigger oscillations in there. So that's I know that is oversimplifying it. There's a lot of theory behind it, but that's kind of like where the what I normally explains to people in a nutshell.
Okay, thank you, Pak Dede. I think it was the last questions for our Q&A sessions. So I guess we are arriving at the closing stage. If you have questions we didn't have time to answer on today's webinar, please contact speakers at the address shown on their slide presentations. We also have a recording of this webinar on YouTube channel, MKI IEPS. Thank you so much for all the speakers, and thank you everyone for attending today's webinar on wide area monitoring, protection, and controlling. As mentioned earlier, today's webinar is the 5th episode of MKI Smart Grid Webinar Series out of 10 episodes, hosted by the Indonesian Electrical Power Society, Masyarakat Ketanaga-Listrikan Indonesia, or MKI, taken place in April 2021 until January 2022. This webinar also supported by PTPLN Persero and sponsored by Tide, Huawei, KEPCO, Hitachi ABB Power Grid, Siemens, ABB Sakti Industry, Trillian, Wärtsilä, LS Electric, GE Grid Solutions, Mitsubishi Power, PT Indonesia Comnet Plus, and in a partnership with Think Smart Grid France and Energy Academy Indonesia, or ECADIN. On behalf of the Indonesian Electrical Power Society, or MKI, thank you for joining today. We hope to see you all in the next episode of MKI Smart Grid Webinar Series that will be held on September 16th, 2021. The topic is Smart Microgrids. So we will keep you all updated on the detail via email. If your company is interested to be sponsor or speaker in the next MKI webinar series on Smart Grid, feel free to contact us at mki.secrt@gmail.com. Thank you and have a great rest of your day. Thank you for all the honorable speakers. Wish you all another safe and healthy week. Thank you very much, Pak Suroso. Pak Dede,
Thank
Mr.
you.
Sankara,
Stay safe.
Thank you,
Mr.
Pak.
Christian.
Thank you. Stay safe and healthy.
Thank you so much.
all. Thank you, Patri.
Thank you all.
Pak Dede, Pak Sankara, Pak Christian.
Terima kasih Pak Tri, mohon izin untuk meninggalkan. Sehat-sehat selalu semuanya.
Okay, thank you.